I will talk about mutability, and I will just try to make a point where I believe that immutability is key if you really want to have arrays and fast arrays in your programming language, and that you should not give the mutability or the responsibility of the resources to the programmer. So the scenario really that all this is about to say if you're the programmer sitting there and you wonder, should I mutate or should I not mutate? That is the question. What should the answer be? And very often, if you talk to a beginning programmer, it is a very simple answer. You say, oh my God, it's so complicated to figure out what the algorithm is doing and whether it is doing what I want it to do. If I don't have to deal with memory, please spare me the hassle. And then if you talk to students that have gone through the pain and have done low-level programming and have started to understand a little bit more what is going on here, they say, yeah, but I have to deal with memory. My system has memory, and so I want control. I'm not willing to give the trust to, say, even very smart people like Dan and Elton, right? No, I don't trust these people, let alone this Bodo guy. I really want to have the control, and then I can do much better stuff. And then if you start to talk to people from HPC, they are even more radical. Right? They most likely say, oh, you functional guys, you're completely nuts, right? I need assembly, because I need full control. And the point that I'm trying to make here is actually, yes, we can trust the compiler, at least in the context of array programming, and immutability actually is the key to performance here. And that's the point that I'm trying to make. No technical nitty-gritty details, but a couple of things that I have come across over time. Now, coming to something completely different, sorry, it's not going to be ML, but it is a different programming language called single assignment C. It has some communality, minimal communality with ML, that is, it is strict. It looks like C, it feels like C, but it's purely functional. And if I say purely functional, I know, many people will say, oh, but you don't have higher order functions, so it can't be functional. Sorry, no, we don't have higher order functions. If we would have higher order functions, we would try to compile them away before we even start. So, you may envision that we have some form of higher order function, like higher order function in Futalk, and we just would compile them away, and then you end up with a language like this. And purely the reason was that we are really, really interested in performance and parallel performance, high parallel performance. That's the goal. And we want to make it accessible to a wider public. Now, I always advocate and say, oh, it looks like C, it feels like C, and it behaves like C. That raises immediately concerns by the purely functional hearts in the audience and say, how is that even possible? Well, because I steal away the notion of memory. There's no pointer, sorry, doesn't exist. All data structures, in fact, are n-dimensional, immutable arrays. Okay. So instead of giving you slides and stuff, what I will try to do is I will run a Jupyter notebook here, if I get my cursor back. Hello. That's a... No, I need to get that thing up there.
Is that going to show on the slides?
That's why I'm a bit... Oh, it's on the... Oh, I see. No.
Yeah, there. If you do that, that's not going to show there.
Yeah, I have the... No, it's...
Oh, you got it?
Yeah, if you... Where's some... Well, I should have tried. I have the preference manager there as well. Okay. So down here.
Perfect.
And then I should be able to rearrange this, right? Most likely do something like...
Hang on, let me try. Yeah. Where's the...
It's always the same. Sorry. I think...
mirror. Yeah, there we are. No?
No. I think you have to drag them. Yeah, there we go. Hey! Oh, fantastic. Okay. So let's see whether we get this done. So See, so I hope it's visible at the back. So we pretend to be REPL, but in fact we are not. So if you just whoa, interesting. In fact, if you just put in a scalar value like 4, then you will see that you get back something that gives you a dimensionality of an array and a shape, and it says, okay, the shape's empty, the dimensionality is 0, and the value is 4. Now, there you see, it is already kind of a little bit different. Now, I can give you a vector of 2 elements, 1, 2. Dimensionality is 1, shape is 2, elements 1, 2. And then I can start, assigning things. I can, for example, say x is 1, 2, 3, maybe. Right, and once I've done this, I can look at x. And yes, it is what it is. Now comes the interesting part. I can also do something like x comma x. So it's now kind of a vector of a vector, which I write down. And you see it's a 2-dimensional beast all of a sudden. 1, 2, 3, 1, 2, 3. Okay. Now I can do an in-place modification. I can define a variable first of all. Let's define a variable y, which is this 2-dimensional thing now. So here's my y. And I can, for example, modify x at position 0 by 42. Right? Modify. Didn't I say immutable? That's weird, isn't it? So I look at x now, and x is, well, it is 42, 2, 3. That's not really surprising. Now, the interesting question is, will this have an impact on y? Hopefully not. And indeed, no. So you see, if I were to talk about memory, this would all be horribly difficult, right? But I don't, and that's very nice. And I can do really crazy stuff. I can, for example, say I want to select the first element of y. So you see, y is a 2-dimensional beast, and I can still select the first element, well, which actually is the first hyperplane. So what happens here may occur to you as being very natural, and indeed I would agree with that statement, but actually what is happening behind the scenes is a bit more tricky. Because we internally have an isomorphism between an n-dimensional array and an n-fold nesting of a 1-dimensional. So by being able to doing these selections, you can switch between the nesting of the expressions that you have on the inside. Okay? And then you can define functions. So let me do one final thing. Let's define a function. And yes, we have some wonderfully weird types. So this is the return type in star. And in star means not it's a pointer to an integer. No, it means it's an array. And I don't really, it's an all quantified shape almost, right? So I want to define a function add that takes 2 parameters, a and b. So this is now 2 arrays of unknown shape. And I can return, and you see it smells like C, it tastes like C. And now what I want to do is I want to have an element-wise addition. Okay, that's fine. I say for any index vector, it's not, because I don't know the dimensionality. So any index vector, I actually want to select the corresponding elements in A and in B. And I want to add them up. And that's my definition. Right? So now I have an addition function, and I can actually write something like add y to y. And lo and behold, this has worked out. Now, if you were to define this in your resource-aware programming language, this actually is already very challenging. Why? Well, it is challenging because you would have to decide, where does the result go? Does it actually go into the memory of A or into the memory of B? Or do I have to allocate something fresh? And obviously, this could be an array that is a gigabyte large, right? Each of this. So that's a difficult choice. And to make matters worse, once you have made the choice, you have to keep this in mind. And whenever you apply this function, you have to think, okay, am I going to modify the first argument or the second? Or, well, what does the function do? Or you may have to have 3 variants of this function. Oh, so from a programming perspective, I hope this kind of explains why I would really like to have immutable arrays. Now, to show you the rank polymorphism, so the ability to define this kind of function that takes any dimensionality, we can do something really funny. We can say we want to add up the first row of y and the second row of y, and hopefully this gives us 2, 4, 6. Right? So we can play with these things arbitrarily, that gives us a lot of expressiveness, of expressive power. So coming back to here, we go dark. No, we don't go dark. So what I will try to do in the remaining 20 minutes or so, or maybe hopefully less, I will explain how we achieve these 3 goals and how they interplay with the mutability aspect of the language, or more precisely, the immutability aspect of the language. So I will start with the productivity aspect, and that is essentially the power of rank polymorphism. So if you would ask me why I believe in rank polymorphism, I used to say until, I don't know, 5 years ago, it's genericity. Oh, you can define operators like this add, which can be applied to any dimensionality. So you can write way better algorithms because you can combine things without having to explicitly say something about dimensionalities or sizes. It's just more powerful. You can write APL-style code. But as of recently, it has become much clearer to me that the real power of rank polymorphism actually lies in the ability to reshape arrays. What I mean by reshape is, if you have a vector of 16 elements, and you have seen this, no, I haven't shown you that. If you have a vector of 16 elements, you can look at it as a 2-dimensional matrix 4 by 4, or at a 4-dimensional array of shape 2 by 2 by 2 by 2. Now, what is that good for? Well, I will show you. So here's one example that we have investigated kind of last year or the year before, scans. Well, it's a simple mathematical problem. You have a vector of elements, aj here, and you want to compute a new vector of the same size, and at any position I, you just sum up the prefix of this vector up to that position. And we start with a 0. For that reason, now we put this into code, and we are stupid beginner programs or unexperienced beginner programs. So we say, okay, we take an n-element vector here as an argument, and we return 2 things, an n-element vector and a number. And then what we say at any position I should have called this j here, I have just mixed them around, we sum up all the elements aj as long as aj is smaller than ai, and then I. And we do that up to all the elements, and finally we return the sum of all the elements. Easy, huh? So why do we need more than 1 dimensionality? It's just a vector problem. What the poop is this guy talking about? Well, now I have to put on my high performance hat, and then I immediately have headaches. I tell people you can write as you want, put your math into code. Beautiful, isn't it? But if I compile this into code, then what I see here is these things, these curly brackets, or tensor comprehension as we call them, they are implemented in parallel. Oh. So we have n summations that are all done in parallel now. Oh, this is horribly inefficient, right? Because we have no sharing whatsoever, but we have concurrency all over the place. Oh, damn. So now, the devil, the second argument of my initial programmer, would say, ha, see, told you, right? I need control. Okay. Let's think what we can do. So first thing we can do is we can say, okay. We can have a sequential implementation. After all, what looks like C works like C, right? So here we go. You just use a for loop. We can do this. We iterate over the shape of A, well, which is actually n here, and then we, do updates on A. And we trust our system. Immutability means, the A that we have here is replaced by a new A for the next iteration, so that is fine. Okay. But then my performance head again gives me headache, because here we have now maximal sharing, but no concurrency. Oh my God. So it seems, actually, we can do something like concurrency engineering straight away. So, okay. If we can do concurrency engineering, let's do this. So we have a vector, and then we turn this into 2 chunks. And because our universe is n-dimensional, here we say, okay, we make it a 2-dimensional matrix, which is 2 by 4 in this case. And now we can have our sequential scan operate on the rows. Okay? If we do that, it looks like this. Well, because we have the sum before the 0th element, the first element is always going to be 0. So here we see 0 and the 0 plus 1, 0 plus 1, 2. And then we have the overall sum of all these 4 elements. Okay, how do we get to the overall result? Okay, let's have a look. It looks already kind of good, but this sum needs to be somehow added down here. And if we would have multiple of those, then we would have to add this for the next row. So what we actually can do, we perform a scan on this vector now. That gives us 0, 6, and 28. And then we use this vector to actually adjust our previous result. So we add this vector so that the 6s are being added down here, the 0s are being added up here. So we obtain this. And if we reshape this back, woohoo, the miracle has happened. We have our scan. Ooh. Now we are rank polymorphic, right? So let's put this into action. So here's the sec code that does exactly this. I've given you the picture from the previous slide so that you maybe have a quick idea. So here, up here, here's the exciting part. We do the parallel scan over the rows, right? We pick an individual row here. IV is going up to M, so we either take the 0s or the 1st row. Then we have a recursive call. Recursive call. Ka-ching, ka-ching, ka-ching. Well, but this is just a call to the sequential version that we just had. Right? Okay, so this is a sequential scan that is done in parallel. Once this is done, we do the scan over the MS values, right? And that gives us this vector MS here, which we use in order to adjust our A, and there's the result. Now comes the miracle. The miracle bit is we change this into a rank polymorphic version. So rather than saying this has to be 2-dimensional, we say, well, we actually, it can be larger. How large? Well, actually, I don't care. What this notation in red here means, it means this is an arbitrary prefix that has n dimensions. And the shape of the prefix is shp, bound by the variable shp. And that's what we do. And the miracle is the other code remains unchanged. Right? So what does this give us now? Well, it actually gives us, depending on the shape, a very different behavior in terms of concurrency. And it turns out that this contains almost all well-known formulations for scans. In particular, Blalo's algorithm as well. If you're interested in those details, have a look at the Array'22 paper that discusses it. Now, the interesting point from coming back to the question of mutability is now, think for a second, you would have to deal with mutable arrays. Now, the recursive call that we make here is on a subarray. Oh my God. So sometimes I operate on an entire array, and sometimes I operate on a subarray. If I have explicit control over my arrays, I have to decide what to do. That means a single version like this is no longer sufficient. Oh, this is a bit of a nightmare. All right, moving on. Another example, I will not go through the details, is we can play a similar game when it comes to blocking. You know, we have been talking about caches. Thank you again, very helpful. So in order to do matrix multiply, for example, you want to do blocked algorithms. That means if you have a 2x2, a 4x4 matrix like this, you would actually like to look at it as a 2x2 matrix of 2x2 matrices, right? So you can achieve this blocking by just a two-liner, and then you have blocked matrices. Okay, what does this mean? Well, if we look at a matrix multiply, a naive matrix multiply, most likely all of you can understand it, even if you're not a aficionado yet, right? It's just an m by n by p, and we get an m by p back. You see a single tensor comprehension here. While not really, on the inside we have this is the scalar product, and this is just saying for all indices ij, we have this inner product. Now what you can do is you can say, okay, if you give me a blocked version as arguments, what I really would like to do, instead of having a multiplication here, I would like to have a matrix multiply there. So all changes are in red. I say, okay, this is bigger dimensional. Okay. And here I call matrix multiply recursively. The beauty of this is, well, this is a full implementation of tiling. What kind of tiling? Well, as many levels as you want. Why? How? Well, you encode the tiling in the shape. And again, we have a situation where the matrix multiply may get an entire array or a subarray of sorts. You know, try to do this when you want to handle memory explicitly. It's not going to be any fun, I dare say. So the real insight is you can have a tiled algorithm as a, 6-liner or 8-liner, and it's arbitrary tilings. You don't even nail yourself to one particular tiling, because the tiling is encoded in the shape, not in the code. And it only works because we have a shape recursive formulation here, which gives you a headache if you want to be explicit with the memory. Now, if you're interested in more details, we had a paper on FHPNC this year, and we actually show that we have blast performance competitive with MKL. Right? So it's multi-threaded execution, super high performance from this kind of specification. Yeah? So, if I may have a quick fazit. If you have mutable arrays, then you have to make unpleasant choices. So you don't really want to do this. We saw it in element-wise addition already. If you have rank polymorphism, and you use rank recursive algorithms, you can write super powerful encodings. You can do concurrency engineering, performance engineering, all that without thinking about the memory, right? And if you want to do this with mutable arrays, it's going to be a pain. because you have to figure out whether you are dealing with a shared pointer or a non-shared pointer, who is gonna release things when and why. So conclusion is programmer productivity, immutable arrays, great, right? Well, there's many occasions where programmers wish to have certain things. The question is, can we deliver ultimately? But my argument, so let me quickly, super quickly, browse is think about optimization. I just give you two stupid examples. That code removal, right? So I give you this snippet, and generate is just allocating an array and filling it with some data. And then you have a call foo that takes A, and it returns an X, but you return A. Question is, can I get rid of this? Well, not quite sure, right? Because what if foo does something to A? If A was mutable, this could happen, right? But I have the guarantee A is not mutable, so I can just blindly chuck it out. Common subexpression elimination, same story. You know, you see foo of A plus foo of A, okay. Ooh, if it's mutable, maybe I can't do a thing. I could have an analysis, if I have foo available, I could have an analysis and say, oh yeah, you're good, you can do this. But here I don't have to do that, I don't even have to think. I can immediately say, yeah, sure, I compute foo of A once and that's it. Because I'm side effect free. Immutability is, opening up the doors. Let's talk for a brief second about concurrency. So one of the cool things of this language is that these tensor comprehensions are inherently parallel. They are kind of map-like thingies. Now, if you would write this and you wouldn't know that A is state-free, then it's not even clear whether concurrency is admissible. Because if I do a side effect here, the order may matter. Oh, bloody hell. It would all go down the drain. So, essentially, it all looks good, right? Better programmability, better optimization, easier parallelism. Yay! But as always, there's a but, and that is, how about destructive updates, right? Now, here I simply piggyback, on essentially the ideas of reference counting. Now, what we do is reference counting to the rescue all over the place. We only do reference counting, and if Simon still was here, I would tell him, no, we don't have cycles because we can't construct cycles because we don't have any closures at runtime, and we don't have any self-referring data structures. And what can happen here, even if we are very naive? Well, it could happen that when we call foo, there's more than one reference to A. So in the first iteration, it might happen that we actually have to copy A here. But once the first iteration is gone, all subsequent iterations can be done in place. And we figure that out. If you have a situation like that, we break up the loop, we do the first iteration with a potential reference count operation. All subsequent iterations we just do blindly as destructive updates. So there's a lot of related work that pre-exists. And, talk to these two gentlemen if you want to have further convincing that this is possible. So let me briefly conclude. So I would like to make a strong claim that immutable arrays, at least, are an asset, not a burden. All right? It is fantastic for the programmer. It is fantastic for the person that tries to optimize your code. It is key to get data parallelism, and it is key to get real HPC performance. And I don't mean linear scaling of something that is slow. I mean real, close to the peak performance of the architecture. And you can run the same code without any modification on various different platforms, from shared memory to GPUs, MPI, or experimental hardware. Thank you.
Very entertaining talk. Thank you. I really enjoyed it. One of the immediate problems that somebody might run into is when they do need fine control over memory. And maybe a concrete example of this would be, maybe I want to implement a high-performance concurrent parallel hash table, something like this. Is it completely outside of the realm of this programming model? Because I need to be able to say atomic updates and these sorts of things in order to do that data structure. And it's okay if it's outside of the model, but I'm curious, is it possible?
No, well, here in this model, the idea is because the only way to introduce concurrency is through data parallelism. So we have a clear control over that, and we can have a static inference of the lifetime of all our variables. So in that sense, there's not a problem. One more.
I was wondering what your approach to sparse matrices. So if you have these, mega sparse ones, how does that fit in with balancing memory density versus taking advantage of SSD and all the other things?
I would love to perform some research in supporting natively sparse matrices. For the time being, the way to go is use the same tricks that all the imperative guys use. That is, you have compressed row storage, say. That means you have 3 arrays that you use in order to do it, and then you can express all your algorithms in the same way. But for the time being, you personally have to translate your sparseness into parallelism, and into the dense representation that we have.
Thanks.
Pleasure.
Okay.
Thank you.